Thank you, Mr. Chairman. Thank you also for the organizers for the kind invitation. So the title of this presentation is Organic-Based Photovoltaics at Extreme Temperature Conditions. I will start with a short introduction on the relation between lifetime and temperature and why, and present some arguments why it could be interesting to deviate from protocol test temperatures and use non-conventional, more extreme temperature conditions to study organic-based photovoltaics. In the central part of the presentation, I will give a review of what our institute have been doing the last few years on the relation between temperature and morphology, and I will end with some conclusions. So, organic-based photovoltaics is showing an enormous increase of efficiency in the last couple of years. So it's really an amazing period that we're all facing. And this makes also that not only the increase of efficiency is of importance, but also increase of lifetime. Certainly, if we would like to match with the 25 years of warranty that we see for our silicon concolleagues, we need to make an important step forward concerning the lifetime. The challenging things related to lifetime, we have heard it already in this conference, we are facing a multitude of failure mechanisms. A multitude of failure mechanisms also induced by a multitude of stress parameters. We've heard about the effect of oxygen, the effect of UV light. We can talk about the effect of humidity, but what I would like to talk about today is the effect of temperature. So how is temperature influencing the lifetime? Within ESO, very nice work have been done in defining protocol test temperatures with temperatures 65 and 85 degrees Celsius. Well, sometimes, since we are a university and academic freedom is something that we like a lot, so please forgive me that sometimes we get off these protocol test temperatures, and why can this be important to change, to go to other temperatures? Well, one thing is again, from an academic point of view, if for a specific failure mechanism, a temperature-induced failure mechanism, you really would like to understand how this mechanism is working, you need to follow a kind of lifetime assessment strategy. The strategy that we follow can also be called a physics of failure approach. It consists of several parts. You start with the reliability assessment. It's a black box. You want to know what are the failures, what is the cause of these failures, the effect, the mode, and the frequency. When you understand with several complementary techniques better what is going on in this black box, the idea is then to come to kind of model for this failure mechanism, to come to a kind of mathematical expression where you bring in all the stress parameters and you can come really to a kind of time evolution of this mechanism. And so finally, when you have this model, you can come to this lifetime prediction, that you really can predict what will be the lifetime after several years of operation. So if you are studying temperature-induced failure mechanisms, obviously temperature is a crucial degree of freedom. That can be important if you study Arrhenius-like behaviors as the one presented by the speaker before. I would like to show you some example, again a kind of extreme example that we studied many years ago from a totally different field, but just to give you a flavor. Electromigration is a degradation that occurs in thin metal lines that you have in your computer. Since they are very small, if you send current through it, you have a very high current density, and that can really blow away metal from one side to the other. This effect leads to a change of resistance, and this change of resistance, you can see here, the rate of resistance change is very small, 1000 ppm, so very small changes. If you want to see this in an accelerated aged manner, you really have to go to very high temperatures. These measurements shown here are measured at temperatures up to 300 degrees Celsius. But the nice thing is, for all these measurement points, we were able to really make a nice fit using this model, where we have the temperature that is related to this degradation with this activation energy. From these measurements, you can determine this activation energy. As mentioned before, it's a crucial parameter for lifetime predictions. So this is a kind of approach. Certainly if organic solar cells or organic-based solar cells are moving to more stable solar cells with smaller degradations, these types of Arrhenius approaches can be meaningful for the future. A second argument why to deviate from protocol test temperatures is because these protocol test temperatures are relevant for a normal window of operation. So you can imagine if you go to more extreme applications that you also need more extreme test temperatures. Let's present to you a first extreme condition. This is the Princess Elizabeth station in Antarctica. It's a Belgian research station, and it's the first zero-emission research station. The founding father is here Alain Hubert, an honorary doctor of our university. And where does this very nice building get his energy from? Well, for a very large amount from solar energy, silicon solar energy. So the question from Alain Hubert was, since you're working with this new type of solar cells, which have a low weight, so for remote regions this could be really a benefit, how do they behave in these kind of Arctic environments? So we just started with some introductory experiments. We tested commercial flexible solar cells from OPV, amorphous silicon, and CIGS, and we went from room temperature down to minus 25 degrees Celsius. So it looks quite extreme, minus 25 degrees Celsius, but when we look to the temperatures on the South Pole, well, in the summer, minus 25 is quite hot because the temperatures go between minus 20 up to minus 60, minus 70. So also for this kind of applications, you understand that you need non-conventional test methods. If now we go to the other extreme, it's presented very recently at a PV conference in Amsterdam by people of ESA ESTEC. Since organic-based photovoltaics are increasing very fast in efficiency, perhaps also applications in aerospace field can come as a possible application. And here I just give you the ideas of what are the conditions. So for this BP Colombo mission to Mercury, the solar cells have to have a maximum operating temperature below 200 degrees Celsius and thermal cycles between minus 170 and plus 215 degrees Celsius. So also this extreme applications can have extreme conditions. And since organic photovoltaics or organic-based photovoltaics is going very fast, perhaps in the future we can see also these kind of applications. This brings me to the central part of the presentation. What is now the relation of temperature with morphology? Because temperature can have many effects. Here we will focus on morphology. Has temperature an effect on the morphology of polymer fullerene solar cell or perovskite solar cells? Just to start with the most recent one, what you see here is a solution deposited film of perovskite. You can see here the morphology that we got. If you look on top with SEM, you see these grains. It's not very flat, but this is kind of morphology. So also there, since the efficiencies are quite high, people are doing a lot of effort to understand also there how the degradation is occurring. And what we've seen, if we go to 85 degrees Celsius in ambient conditions, also there we see some changes of morphology. I don't know if from your side you can see it, but on the morphology you see that there are some additional features forming. It's like these trackers with some seeds on top. That's what we are making when we bring these perovskites at these temperatures. For the polymer fullerene organic solar cells, also there we know for several years that also their temperature can lead to significant changes of morphology, where we have, for example, big needles forming. Where are these needles coming from? Well, these needles come from PCBM. PCBM that can be quite mobile at high temperatures. So what happens at high temperatures is that here is, after 2 hours, a TM picture of a film submitted at 110 degrees Celsius. This is for P3HT PCBM. After 4 hours, after 8 hours, you see how your nice, ideal nanomorphology evolves towards these kind of chunks. And what are these chunks? This is the PCBM that comes together. So you can also imagine if your morphology changes, that also your current is changing, and this is what we see here, measured at our extreme conditions, 90 degrees Celsius, 100 and 110 degrees Celsius. But this temperature has not only an effect on morphology and the short circuit current, but also on the VOC and on the charge transfer energy. That's what we illustrate here. VOC goes down if we measure it in situ Fourier transform photocurrent spectroscopy, the energy of the CT state. Also there we see that a change is occurring. And what we have provided as an interpretation for this fact is that if you have this phase separation, you have more ordering occurring, and when you have more ordering, you have more band broadening, and your effective band gap becomes smaller. So temperature has an effect on morphology and affects also the ECT and the VOC. The two previous images were obtained when we submitted these films to elevated temperature but in dark. What happens now when you put light on it? So again, this is what you have when you do the annealing in dark. When you do now the same annealing at the same temperature but you apply light, you see that no phase separation is occurring. So for us that was quite a surprise. We were not the only one seeing this. At the same time, also the group of James Durrant and Imperial College saw these effects. How can we interpret this? So the interpretation that has been given for this effect is that we have a kind of light-induced dimerization of PCBM. So the PCBM dimerize and become more fixed, and so the mobility goes down. So that's quite positive, this in relation to morphology and stability. So the dimers inhibit the PCBM to crystallize, reduce the phase separation. You can do also light pre-treatment at room temperature. It's not only observed for MDMO PPV, but also for various types of polymers. The only thing that we have to be careful about is now we don't have to have the feeling that everything is solved, because if you go higher in temperature, these dimers dissociate again. So if you go higher in temperature, you see that this effect is cancelled out again. Are there solutions? Well, very recently, Ilaria Cardinaletti from our group made a kind of mini review toward bulk heterojunction polymer solar cells with thermally stable active layer morphology, where she nicely reviews these temperature-induced phase separation effects and various possibilities to solve this problem. Within the Institute, several routes have been investigated to solve this or to inhibit this phase separation. Some of the routes followed weren't successful, but a number were quite successful. We've seen that by increasing the glass transition temperature of the polymer, the donor polymer, we really had a dramatic increase of the stability. Also, many years ago, we started with introducing functionalized side chains to the donor polymer. Also, this was quite a successful approach. I just mentioned the light-induced PCBM dimerization, and then we looked also to other approaches. What I would like to do now is to show some further recent results on this sidechain modification. This is work being done in the PhD of Jürgen Kester. Kestis. So very recently he published in Organic Electronics this introduction of side chains on P3HT materials, and what he's shown that even with bringing in just a small amount of these side chains, 5 to 15%, a dramatic increase of stability was obtained. Very, very recently, he also used this approach to the to PCPD-TBT. So also there he introduced these sidechains just as a proof of concept. And what he's shown there is that if we look to the IV characteristics of these solar cells with these sidechains, a small amount of sidechains, these sidechains didn't alter significantly the IV characteristics, so the solar cell performance was not damaged by that. Also very important, since we're talking about extreme temperature conditions, if you look, for example, at this sidechain modification, the TG was brought up to 213 degrees Celsius. So this is really an extreme high TG material. How do the initial results look like? What we see here is measurement 650 hours at 85 degrees Celsius. Here we have the normal, in black, the normal PCPD-TBT, and here the two ones with a sidechain modification. And you can clearly see that with the sidechain modification, we have an important improvement. Still, if you look at the initial part of the curve, also there we have this dramatic decrease, and the question is, this initial loss in VOC, for example, is this due to the light-induced soaking, as published recently by Foroshasi et al. And presented this morning in an excellent manner by Thomas Hümmüller, and the degradation and the short-circuit current, is this due to bulk degradation? So this has been done in dark, I told you, but to measure, to get these curves, of course, we had to put light on a regular base. So although the intention was to measure in dark, these materials received a lot of light. So what we've done is we put these devices really in the dark for 25 hours, and we looked to the IV characteristics before the aging and after the aging. And there we have seen that aging in dark confirms that the losses in VOC are light induced. So the change of VOC is really due to the application of light, and the change that we've seen in the fill factor is not light induced. But this has to be studied further. So as a last point, I would like to come to the aspect of lifetime prediction and Arrhenius. So if we go to the ancient model system, MDMO, PPV, PCBM, where you see this kind of phase separation, what we've done, we looked at the short circuit current at various temperatures, and we said this is an effect where PCBM moves, so it's a kind of diffusion effect. Diffusion is often described with the square root of T. It's a thermally activated effect, so we bring in also a K parameter that is related to temperature. And what do we think that the relation to temperature could be? Such an Arrhenius relation, so this K is related to temperature through this activation energy. Well, if we fit these curves, we can do it very nicely with this formula, and you can retrieve very nicely an activation energy of 0.85 electron volt. So with this activation energy, you can really fit all these measurements between 50 and 90 degrees Celsius. But the idea is that you could do also prediction to another temperature. So if you do a prediction to a room temperature, for example, this would be the curve that you get, and the points that you get on top are the points that we really measured. So this gives you an idea of how this approach can be used really to do lifetime predictions. You could go also the other way around. You could say, let's predict what happens at 120 degrees Celsius, at 150 degrees Celsius, and so on. But there, you have to be careful that Arrhenius is only valid in a given temperature window. And that's what I would like to illustrate in the last slides. So what we see here are images of P3HT PCBM that have been annealed in the dark at various temperatures. Here you see 2 hours at 100 degrees Celsius, 2 hours 125, and here at 150. And what we see is that the crystallization is slower below and above 125 degrees Celsius. So although that we are at a higher temperature, this phase separation is not going faster. So it's a little bit a crystallization anomaly, so it's counterintuitive. How to understand that if you go higher in temperature, this crystallization is not going in the direction that we need? Well, to investigate that, we work together with our colleagues from the VUB in Brussels, where they have advanced thermal analysis tools. They use the so-called rapid heat cool calorimetry, where they studied the crystallization enthalpy for these various materials at isothermal conditions. And what they've seen very nicely is that if you look at the crystallization rate that comes out, this crystallization rate becomes maximum between the melting temperature and the TG. And that's also what we see, this behavior that we see from kind of phase diagrams. We see it in the images of our phase separation and comes also back when we look to our IV characteristics. So be careful when you accelerated aging tests are very meaningful, but watch out, do it only in the temperature window where they are still valid. So, conclusions, why go to extreme temperature conditions? Well, you can do it if you have extreme applications, new applications for this field. Playing around with extreme temperatures can be very interesting if you want to study really in detail what degradation mechanisms are, what the physicochemical mechanism is in relation to temperature to come to a mathematical formula. We've seen also that the morphology of perovskite and bulk heterojunction solar cells is not stable as a function of temperature, and that the temperature affects the PV characteristics and the current and the VOC. For the polymer fullerene solar cells within the Institute, several routes have been proposed to improve this stability. We've seen that increase of TG can be very successful. Could also be that this TG determines your upper temperature for your operation window. If you say, organic based solar cells, which temperature window can you use it? Could be that the TG is the upper limit. We've seen this light-induced PCBM dimerization, and that the incorporation of alternative side chains can improve also the thermal stability of the morphology. And in terms of extreme temperatures, it has been demonstrated that also a TG of 213 degrees Celsius has been reached. Finally, I would like to thank our star players that have all contributed to this work. For the polymers, Dr. Lutze, who is present over here, Professor Maas, Professor van de Zande. For the thermal analysis, Professor Van Assen and Van Mele of the VUB. This for the funding. And for the people who, after Barcelona, go to Lille, they are also invited to join us in San Francisco, where there's a very nice symposium, organic-based photovoltaics. It will be the last time that will be organized in San Francisco. And also there we look at the focus on increasing the reliability and lifetime, but also what happens on hybrids, organic-based photovoltaics. Thank you.
Okay, thank you, Manca. There's time for a few questions. Eugene?
I have two questions. The first question is, can you say a couple of words about what's happening with perovskite? In organic, I understand the phase separation. In perovskite, there is no phase separation, it's just one material, so you have increased grain size. And the second question, what's happened with MRAs in San Francisco?
So the first one, I just added these slides because Esther asked me this morning, are you going to show something on perovskite? I was not intending to do it. These are just initial experiments that we are doing. So it's even not published yet, but what we see is that this is being done in air. When we do it in air, we see this effect. When we do it in nitrogen, we don't see it. So it's also related to your ambient temperature. The second thing is MRS this is filmed, so MRS had decided for a very intelligent reason to move the spring meeting from San Francisco to Phoenix in the future. So this will be now the last time that the MRS spring meeting in the States will be organized in San Francisco. From next year on, it will be in Phoenix.
Are there more questions?
Could you maybe comment on the other parts of the devices if you looked into that, like the temperature effect on whole transport layers or even the encapsulation itself? Have you looked into that and how the Arrhenius model could be fitted for the entire device in that sense?
So that's the opposite of what we would like to do. If your car breaks down, we want really to see what is the item that broke down, and then we would like to focus on that part. How is there the model, the degradation model for that part? So the approach that we followed here is to try to eliminate all the other effects so that you know what is the model for that effect. Finally, when you have the models for the major degradation mechanisms that are occurring at the same time, then you can bring everything together. But if you look at this aging for the entire device, it's not only a black box, but it's a box of Pandora, because there are a multitude of mechanisms that are occurring, and then perhaps it's possible to get an Arrhenius analysis and to get an effective activation energy. But what does it mean? So now we tried the opposite way, just from a scientific point of view. Can we understand the specific failure mechanisms? What is the activation energy? And then at the end come to the entire device.
Okay, I guess with that we go to the next speaker. Yeah, thank you.